So we need a way to monitor the progression of Alzheimer's disease, and besides the conventional, traditional cognitive questionnaires that track changes in cognition and memory, other questionnaires track limitation in patients' functions of, or activity of daily living. So we refer to functional domain as those activity of daily living that may impair patients' quality of life and are important to patients. They were based on a literature search and patients' advisory board's input, and as such they were selected 14 functional domains and classified in 4 tiers as highly relevant, relevant, neutral, or less relevant. And such classification was made based on the ability of such functional domains to predict conversion from early stage of the disease to late stage of the disease, and also being recognized by the patients as important for them. So there were several in-person meetings with patients that was organized by Alzheimer's Europe. And then the patients were presented with this list of functional domains that were found as important based on literature. And the patients needed to classify them as very important for them, fairly important, or not important. Patients were also asked whether in between those that were selected, functional domains selected from the literature, whether there was something missing, and they could add that to that list. So there were these 14 functional domains selected. 3 were classified as highly relevant. Those were difficulties at work, difficulty in navigation and memory, difficulty in planning skills, and also the memory required to complete a task. 6 were classified as relevant, 4 as neutral, and 1 as not relevant. And among those that were classified as relevant, there is, for example, difficulty with finance and also sleep quality. So once the functional domains were identified and classified according to their relevance, so there was a group of experts that would look for devices, so remote monitoring technologies that could track changes in those functional domains. So there was a group of experts that identify those devices, validate them, and then choose them for the context of this trial. So the data that are produced by these kind of technologies is very different in nature than the data that is usually collected with paper and pencil by a doctor. In such questionnaires, so the traditional questionnaire, you may ask whether the patient has been able to do a task, and the answer to that question is yes or no, while the data coming from these devices collect information in a more dynamic and continuous way. For example, if the traditional questionnaire would ask whether the patient is able to do a financial transaction, the device, the banking app that has been developed, will be able to test that ability of the patient by simulating the time that the patient needs to do that transaction, or for example, the many times that enter the wrong PIN. So it is a more dynamic way of collecting information on those activities of daily living. So this kind of data is much more complete than the passive information that we collect through the questionnaires, and we hope that that would be also more sensitive to track changes. But we need to be aware that different kind of data may need different approach to be analyzed, different methodology. And the classical statistical tools are not always adapted to this type of data. So it is here that machine learning and artificial intelligence is very important and come into play. So the REDAR-AD data has been analyzed using classical statistical approach, but also machine learning and artificial intelligence tools. And here my colleagues Manuel and Holger will explain what they did in the context of REDAR-AD.
So in essence, the thought, first of all, was that opposed to classical statistical approaches, which typically look in one particular feature of a data set individually, with machine learning models, you can in essence combine a variety of different variables and features jointly and then try to see whether there is an ability to discriminate between different diagnostic groups. So in this particular case, we applied different machine learning approaches from classical machine learning methods indeed, so such as XGBoost, random forest, and penalized logistic regression, over also to more advanced ones that comprise also only from our own group developed algorithms. So at the end of the day, what we found with these methods is indeed that several devices allow us to discriminate indeed relatively reliably between different diagnostic groups, and they also, in essence, allowed us to gain more insights how different variables might actually depend on each other and how the variables or features that you can extract from such device technologies might relate further to what classically is assessed in clinical studies.
Yeah, in the second work stream, we didn't focus on the discrimination of the different diagnostic stages, but rather on a better understanding how the features from the remote monitoring technologies are related to classical questionnaire-based assessments. And for that purpose, we applied a special algorithm named Variational Autoencoder Modular Bayesian Network that was developed in prior studies. And this allowed us to generate a graph that shows the relationships between the T-derived features, the diagnostic stage, and several clinical scores. And in conclusion, we found that there is no one-to-one correspondence between the clinical scores and the T-derived features. So essentially, they measure different things.